j'y prenne goût, faut que je réagisse. Non, je ne suis jamais seule. Avec ma solitude.
Who's doing the, how are you explaining the balloting process?
Like, I'll give the test of time award and Christoph will do the best paper award. Unless you want me to take the number 2 winner. Like
I'm just wondering who's, are you
I'll
explaining
do a
the
little bit of
ballot?
moderation about the ballot.
Oh, yeah. Christoph.
Okay, you can just type that.
J'ai autant après que j'ai versé de larmes. Si parfois je la répunie, jamais elle me désarme. Et si je préfère l'amour d'une autre courtisane, elle sera à mon dernier jour, ma dernière compagne. Je ne suis jamais seule. Avec ma solitude. Non, 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 non. Je ne suis jamais seule.
Check 1, 2. Okay. All right, well, good morning, everybody. We're going to get started here with our last day. And before we dive into our first paper session, Christoph is going to review the best paper balloting procedure with you.
Thank you. So, we have a best paper award to hand out today. And at HPG, traditionally, the best paper award is voted for by the audience. To do that, we have prepared these best paper ballots. So in a few minutes, Erin and I will be walking around here and handing out these best paper ballots to all of you, one per person, obviously. And you get to give points to 3 different papers. So you do that by filling in the numbers of the papers down here. It should be quite self-explanatory, I hope. And then we want to do the counting right after this session. So please do the voting at the end of this session today. And then return your best paper ballot to either this cardboard box there or the one over there as you leave the session. Then we'll do the counting, and later today in the closing session, we will announce the results. And one more thing, it doesn't really say so here on the ballot, but please do not try to give 3 times points to the same paper. that's not allowed. So that would just make the whole vote invalid. Yeah, any questions? Seems to be clear. Then I'll hand over to our session chair for the last HPG paper session.
Yeah, I am Sung Lee from Seungkyunkwan University, South Korea. I'm chairing the session, probably the last paper session. The last session is about neural textures and encodings. Yeah, and yeah, we have 3 papers, and the first paper is a hardware accelerated neural block texture compression with cooperative vectors. And authors are Lohang or Laurent Becourt and Anis Benyev. And Anis will present the paper. And yeah, they are from the Inter, France.
Does it work? Yeah? You hear me? Oh, cool. Okay, let me just put this here. All right. So I'm Anis. I'm a graphics research engineer at Intel, and today I'll be presenting our paper, Hardware Accelerated Neural Block Texture Compression with Cooperative Vectors. It's a mouthful one. All right, so before we dig into the details, I want to give you a bit of an overview or an opinion on why this is currently relevant to game developers. So video memory footprints, the game memory footprints have been getting a lot bigger over the last 20 years. For instance, the Call of Duty franchise has managed to go from 1.5 gigabytes to up to 300 gigabytes of memory footprints. That's 200 times bigger, and that's a nightmare for everyone involved in those game productions. And there's a reason for this inflation. Game developers just don't do that for the sake of doing it. Visual standards and gameplay expectations got very high over the years, and the quality improvement mostly comes from the assets that these games ship with. So there are 2 main components that scaled a lot. Geometry is the first one, so meshes, animation data, particle systems, etc. And on the other side, texture data, and most specifically, PBR texture sets, which we are trying to tackle here. In the meantime, the major hardware vendors, pushed by the recent trend of ML, have decided to integrate it into their GPUs, a dedicated hardware to do matrix multiplications that are larger than your usual 4x4 model view projection matrix. After a first attempt with cooperative matrix Vulkan and wave matrix DX12, Microsoft recently managed to standardize an HLSL built-in functions to do matrix multiplications and access the hardware-specific instructions, so DPads for Intel, WMMA for NVIDIA, and MFMA for AMD. So ML can definitely help with this hardware acceleration that is available now, but the real question is how exactly should we do that? So first, we're going to define our requirements. Often, PBR texture sets are around 9 channels, so give or take if it has subsurface, anisotropy, or something fancy. And 4K texture sets are also becoming standard, which don't really help with the situation here. In our paper, we don't cover HDRIs, light maps, low-A textures, which cannot be neglected in package sizes, but some other solutions can be used here. So if we take as an example the robot scene here, it has 4 texture set, 9 channel aids that need to be stored and accessed for rendering. The go-to solution for most game productions, at least the one that have to ship on a console, is hardware-accelerated block compression. And depending on the ISV's specific compression tricks, studios will pick their preferred BC algorithm. The issue here is that BC compression is not enough and introduces some blocky artifacts due to the nature of the algorithm. They're really hard to get rid of if you've ever worked with BC algorithm. And by not enough, I mean that it's now a given that even a AA game will not fit into VRAM. Streaming is a mandatory process. And some AAA games start to stream MIP0 content during the game execution from the internet to damage control the issue. So this brings us to the question, what would be the ideal solution? So we think the ideal solution would be a solution that would bring down VRAM usage, bring down disk usage as well, have positive impact over the quality with compared to other solutions, BC or state-of-the-art solutions, would have no impact over performance or ideally positive impact over performance, and would need to support texture filtering, isotropic or anisotropic, ideally using texture samplers. So these will be our criteria for the evaluation of the state-of-the-art. And these methods here on screen are the ones that try to tackle texture compression with ML solutions. So Data's approach requires a texture indirection, and that makes it not viable for game performance constraints. Vadaniatan's approach has a very, very good quality compression ratio, but decompression, performance, and mostly filtering are real issues with the method. Fujida's approach is good as well, but it doesn't bring anything on the VRAM criterion given that it's a transcoding method. Weinreich's method is very interesting, but quality-wise, it's not great, and performance-wise, it has a bottleneck given that it's doing the MLP inference within shaders, either a fragment or a compute. What we propose is an improvement with respect to Weinreich's method. So it improves quality significantly, but it's still not perfect on the performance side. As our method is an improvement of Weinreich's method, we're going to have a closer look at what that method does. So this method operates on the entire texture set rather than 3 or 4 channels at a time. The assumption is there is a strong correlation between the various channels of a PBR texture set, and a neural network is efficient at finding these correlations. The correlation detection targets 4x4 blocks, and the reason for that is being able to take advantage of hardware-accelerated block compression. The MLP is stored as 4 BC6 textures that are MIP-mapped, and the MLP has one hidden layer of depth 16 that is used to decode the PBR channels. The inference, so 3-chain vector matrix multiplications, are done in a compute shader or in a fragment shader using FMA instructions, and the method supports isotropic texture filtering using a texture sampler and a texture unit. So our method can be seen as an improvement, and we build upon this method. So from our experiments, a wider hidden layer allows for a higher quality of the image. So we evaluated that on a data set that we got from the website Polyhaven, so 83 texture data sets. And the size of the latent code doesn't vary that much. So the size of the hidden layer is actually the most impact that we can have on the quality of the achieved compression. We also generate subpixel shifts during the training. This allows us to, and they are applied to the second and the fourth textures of the latent space. This allows us to avoid alignment of the latent blocks and reduce compression artifacts, as we'll see later in the demo. We also modify the latent space structure. This allows us to increase quite significantly the compression factor. And our latent space is stored into MIP-map BC1 textures, and our MLP weights and biases are stored into FP16. We also realized during our test that the method actually also supports anisotropic filtering, even if it was trained for isotropic filtering. So that's a nice win. I invite you to check the paper for more details about this. So in order to illustrate, I'll be using the robot asset from the teaser scene for the rest of this presentation. So in our paper, we explore 2 variants for the network architecture. So variant A has 2 full resolution textures and 2 half resolution textures. With their MIP chain. So this is very similar to what Weinreich does, but with a smaller footprint as we are using an LDR format instead of an HDR format. And the second variant so has 1 full, 1 half, 1/4, and 1/8 resolution textures. So for the sake of clarity, I'll hide the MIP chains on screen, but the training process includes generating those MIP chains, and that's very important. So these latent space textures, when grouped together, form our latent space. And they are sampled using a texture sampler, and they are fed to an MLP that has 1 hidden layer. The size of the hidden layer can be 1632 or 64, depending on your hardware, performance constraints, and quality requirement. The MLP evaluation will produce the PBR channels that will be used for rendering. So it's 9 for the robot, but it can go as high as 16 channels, which is the maximum that we've encountered in the test that we've done. So to be able to generate the neural presentation that will be used later for inference, we have to run a training process that will produce all latent code and our specific MLP for each texture set. On the train assets that I mentioned, so the Polyhaven, it takes 10K iterations to get usable results, 80K to get shippable quality, and we reach maximal quality at 100K iterations. So to be able to reach this maximal quality, currently during our experiments, it takes 30 minutes on a 4K texture sets, but it's done in PyTorch, and it can be quite significantly improved. The quality that we're able to achieve per texture set the quality that we're able to achieve for texture set is inversely proportional to the number of channels that we're trying to encode for that texture set. And we encode, we emulate the BC format during the training process using floating point tensors, and the input and the palettes are stored in FP32. So we do quantization aware training along the process, and a sigmoid function is used to prepare for quantization. On the implementation side, we try to integrate our tech in a representative structure of a modern game renderer. But we also wanted to keep the source code simple, as it could serve as a reference implementation for these kind of techniques. The renderer started with a visibility buffer pass, which is standard now, followed by a classification pass. I'll come back to that in a minute. A gbuffer path that will consume the neural materials, will produce a gbuffer, and that gbuffer will be used for lighting. So most renderers today are tile renderers, so we can actually mitigate the cost of our classification pass in this existing tile pass that is in tile renderers. And the classification pass classifies each tile into 3 categories: background or non-neural, work groups that have a single MLP, and work groups that have low neural occupancy or mixed MLP usage. And those tiles are repacked together for a more efficient inference. So I invite you to check the paper. There are some additional details and implementation code, pseudocode for that pass. And the reason we do repacking is that the hardware doesn't actually multiply a vector by a matrix the same way it does for Weinreich's method. It multiplies a matrix by a matrix. And the size of these matrices are architecture dependent and are baked into the silicon. The cooperative vector extension abstracts this for you, but it can behave poorly if you have divergence in the right matrix that you're multiplying with, which comes from the MLP. Another thing that is interesting to be said is that the API proposed support of many types, but it's not because it says that it does support for a type that the actual computation happens in that type. Each driver or each hardware has a bunch of types that are supported, and it will convert on the fly if that is not supported natively by the hardware. So be careful with that. In our case, the MLP isn't converted to optimal layout for each GPU at upload time. We use that for cooperative vector path, and then we use a regular column major layout for the FMA path. And we evaluate the UV derivatives during the gbuffer pass, and we use those to sample the latent space. Oops, sorry. Come on, sorry. Oops. So that covers it for the inference part. So we'll be looking at some practical results, some performance numbers, and then I'll be moving to a quick demo. So the first comparison that we want to make is our method with the reference method. So we'll be taking 2 variants. Variant A, so 2 full resolution textures and 2 half resolution with a hidden layer of 64. Variant B that has 1 full, 1 half, 1/4, and 1/8 resolution texture. Again, hidden layer of 64. And Weinreich's method, which is our base method. So the first metric we're interested into is the compression factor. The higher, the better, obviously. Both our variants outperform Weinreich's methods, and obviously the variant B has a significantly better compression given that the latent space is smaller. The other metric that we're interested in too is quality. So in our case, we used PSNR, but we'll do some visual checking just after on the slides. This will allow us to evaluate quality. So again, both our variants outperform the reference method, and as expected, the method that has a bigger latent space is able to achieve a better PSNR, but I will see it's not as drastic as it may look on looking at the numbers. An important thing that is worth saying is that Weinreich's method has a hidden layer of 16, so it's not completely a fair comparison here, but I'll come back to that for the next comparison. So PSNR can be a bit tricky to measure quality of textures. So we'll be looking directly at the textures so you have a better sense of the kind of artifacts that are there and disappear. So we start from our compressed textures, which is the best quality we can achieve. This is what Weinreich's method is able to achieve. As you can see, there are some clear artifacts on the gray areas. In the central areas of the pixel, there's a reduction in quality. It's not great. If we move on to variant B, as you see, there's a first clear improvement in quality. All those artifacts have disappeared. The texture is significantly cleaner, and that's really nice. And if we compare that again with variant A, which has a smaller compression factor. The quality has improved again, and if we compare it to the reference, we're actually very, very close for a memory footprint that is close to what WineRush has. The next comparison I want to make is the impact of the hidden layer over the quality and the performance rendering. So we'll be taking 3 variants. So variant B, all variant B with different hidden layer size. So variant B with a hidden layer size of 16, 32, and 64. So the compression factor is the same for all 3 variants. It's twice what WineRush is able to achieve, and it's very nice. And the reason for that is that the MLP itself is neglectable in terms of size compared to the rest of the texture set that we're trying to compress. Then on the quality side, as expected, the wider the hidden layer, the bigger the quality we're able to achieve, which is the whole purpose of this. And finally, on the performance side, here are some numbers that are the gbuffer pass, which is where the inference happens. So as you can see, so the timings, the percentages are timings relative to the hidden layer of 16. So it's a bit slower going from 16 to 32. It's actually quite minimal. It's significantly more going from 16 to 64. That said, this is a pass-through gbuffer, so nothing happens during the gbuffer. So if you have a significantly more complex gbuffer as you would in a game production, so a shader graph with operation happening, the impact in percentage is actually not that bad. In our case, it's just a simple pass-through gbuffer. So again, let's look at the textures a bit closely. So this time we'll start with WineRush, as we've seen the reference before. We'll start with WineRush as a base comparison. So if we go from WineRush to our variant B with a hidden layer of 16, so these have the same cost of inference, small cost of texture reads, but same cost of inference. We're able to get rid of the artifacts in the greatest areas, but some other artifacts appear. Overall, if we compare the PSNRs between the two, roughly it's the same, but it's twice as less memory footprint on disk, which is a nice win. Then if we go from 16 to 32, there's a clear quality improvement, and we're able to keep that compression factor that is very nice. That is twice what WineRush is able to achieve. And as we've seen in the performance numbers before, the overhead is actually minimal on the sampling itself. Finally, again, if we move to hidden layer of 64, again, the quality improvement is visible. It's not as drastic as going from 16 to 32, but if you can afford it, it's always nice to have. And if we compare it to the reference, we're really close, and we'll see that in the demo. The last comparison that I want to make is the rendering time of the teaser scene on 3 different GPUs. So the Intel Lunar Lake V180, the ARC B580, which is a discrete GPU. The first one is an integrated GPU. And the last GPU being an NVIDIA GeForce 4090. So these are the rendering times that we get for a 1080p frame with a hidden layer of 64 anisotropic sampler for the textures. If we use our neural material but use FMA, so no hardware acceleration, the rendering times obviously skyrocket. And if we enable cooperative vectors, we're able to have significant speedups and get back to something more reasonable. So in this specific case, using anisotropy, we actually outperformed the base variant and compressed here, but also BC6. Because we have better cache coherency. But this is really dependent on your render pipeline. This is really dependent on your frame, the distance of the textures. The cache coherency has a lot of impact. So I would not take that as a statement that our method outperforms whatever exists, but it actually does sometimes. So it's nice to take that. So the method is not perfect, obviously. It has some clear limitations. So as I said, it only operates on texture sets. So it's not adequate for single textures. So I said HDRIs, light maps, this kind of stuff. It's inadequate if your texture set doesn't have any coherence inside of it, which is unlikely, but it is still possible. And it's less efficient if you have a very low of channels in your PBR texture set. You have a uniform diffuse. You have some of the channels in the ARM textures that are uniform. It's less relevant, and you get a less significant compression ratio. Obviously, the rendering costs can be non-neglectable depending on your render pipeline structure and the assets and everything. But you can mitigate that using a lower hidden layer, as we've seen, and the impact on the performance, the impact on the rendering quality is actually better whatever exists before, and it's sorry, it's better than in terms of quality what exists before, and the performance overhead is not that bad. So finally, it can be tricky to integrate in rendering pipelines that need to access the texture set at multiple stages of the rendering process. I'm happy to discuss that during the questions or after, but there are some solutions to do that in an efficient manner. Among the things that we start exploring is sharing the MLP between different texture sets. Depending on the texture sets, actually, it doesn't impact the quality that much, and it saves on the repacking process. Obviously, the compression is slow for now. We've started exploring moving away from a PyTorch implementation and accelerate quite significantly the compression process to something that is usable in production. I'll be doing a live demo, so the things I'll be covering is a quality comparison between neural BC6 compression, which is state-of-the-art, and in compressed for quality comparisons. I'll be showcasing trilinear and isotropic filtering of the methods, and I'll be showing some performance numbers of FMA, cooperative vectors, and compressed, and BC6. All right, so here you can find a link that has the inference code, the full source code of the demo. It's MIT, the paper, additional materials, and soon the training code itself, if you're interested. And I'll be just doing the demo quickly. All right, so meet my friend Michel. Michel is a nice dinosaur. He is very nice looking, has a very nice skin, and the reason for that is not because Michel has a nice skincare, it's because Michel is using our neural material model. If we look at the debug view, we're able to see the tiles that have neural inference happening in them, and in red, the tiles that need to be repacked together because they have an occupancy that is too low. This debug view allows us to visualize diffuse colors, normal, other materials, other channels of the PBR material. But for this demo, we'll be sticking to the normal as it's the one where we see most of the artifacts. All right? Good boy. All right. So one thing that is interesting is comparing quality-wise in terms of final render, the difference between the various methods. So this is what we get with our neural model. If we compare that to incompressed, we're actually very, very close. In terms of quality, it's almost imperceptible. This is what BC6 produces. As you see, there are some clear artifacts, and these clear artifacts come from the normal. We've seen that in a couple slides showing BC6 compression yesterday. Our model, and that's thanks to the subshift pixels and the fact that we're sampling multiple pixels, we are able to achieve significantly better quality and something that is actually really close to the incompressed reference. All right, let's come back here. So Michel can be a very enthusiast dinosaur or a very chill one, but Michel doesn't flicker. And the reason Michel doesn't flicker is because Michel has trilinear feature in this situation. So if we disable it and we zoom out, as you can see, it's horrible, fireworks everywhere. And it's even more perceptible in the individual channels, as you can see here. If we rely on simply using the samplers, that solves the issue pretty clearly. And also for the final render. All right. Another thing that I would like to share is anisotropy, the anisotropy impact. So this is what we got for the nearest filtering. Obviously, it's looking good. You get a lot of details, but as soon as you start moving, it's unbearable. Sorry. This is what you get with linear. So it works, but it's very blurry. As you can see, we lose a lot of the details here. And if we move to anisotropy, we're able to get back those details, and the method works well. Again, I invite you to check the paper for additional details and visual comparison with specular highlights and other signals. But yeah, it works actually pretty well, and it uses already existing hardware, so it's a win. Okay, the last thing that I would like to share, all right, is some performance numbers. Yep, cool. So here we're around, I'm sorry, I don't see, probably 0.7. Okay, it's a bit slower because I have two monitors. 0.7 rendering time for this. If I disable cooperative vectors, it goes up to 13, 14 milliseconds. So that's a 20-time improvement. So cooperative vectors are really useful here. And if I move to incompressed, we're around 0.6, 0.7, so it's very similar. Again, that is very dependent on the setup that you have. And if you compare to BC6, again, 0.7, 0.6. So in this specific case, the usage of neural material doesn't impact the rendering time that much. Okay, so that covers it for me. I'm happy to answer any questions that you have regarding this paper and say goodbye to my friend Michel.
So we have time for a couple of questions.
Great talk. Did you notice any difference between different hardware vendors in terms of, let's say, the result, because they use some intermediate precision in a different way or anything?
So precision, no, we haven't noticed anything. Performance impacts, yes. But in terms of precision, they all support F316 natively now, at least the ones I've compared. The third vendor, AMD, doesn't have any public drivers, so we were not able to test. But in terms of precision, not really, no. We get the same result. But we operate in F316. There are some other formats that are available in the cooperative vector API, and maybe for those, there would be a difference.
Thank you.
Any more?
Hi, it's always great to see texture compression. Having actually put a texture compressor out that then got used by artists, they always complained if it took more than if it got up to a minute to compress something, I'd get heat back from our dev tech team, etc. How were you considering to sort of reduce that rather long time down to something which is more interactive?
So it's so there are two things. During their process, they don't have to use directly the final quality. So they can use intermediate quality just to see what it looks in game. But if they want final quality, so either distributed systems or ideally, like we're working on solutions that allow to reduce. So moving out from PyTorch and doing ourselves the optimization somewhere else actually helps a lot with performance with our tests. And we're exploring other things that I cannot share that actually work quite well. So upcoming work that is coming that would help reduce quite significantly, couple orders of magnitude, the compression time.
Sorry, there was one. You said BC6 was state-of-the-art. Wouldn't ASTC be more state-of-the-art? And I know it's not on desktops, but have you compared?
So we went with whatever the studios told us that we're using, and mostly studios that ship on PC and consoles. So ASTC has advantages, but PC is more widespread. So that's why we picked PC for comparison.
Great talk. Yeah. Did you do any comparison using this from pixel shader versus compute shader? How's it performance?
So currently, with the current spec, you can't really use cooperative vectors. In fact, it's going to come eventually in the spec, but we haven't used it because at the moments of writing the paper, it was not supported in the fragment shader. It just compute, so not really. I guess that's going to be tricky for the wave coherency and a bunch of things to be able to repack, isn't that you can do the repack in step. So that may be a challenge, but yeah, it is what it is.
Actually, we have no time.
Great talk. So I think, if I got it correctly, you fit your network for the whole texture. Would it be beneficial to just fit for the parts that are actually used by the UV coordinates, basically overfit for these parts and ignore all these like wide areas? Would that help?
Then how would you access time? How would you access the parts that are less useless?
No, I'm talking about the parts that are not used at all. I think you optimize for everything, right?
Oh, you mean if they are, that means you would need the UV coverage of your mesh to define which part of the textures you take into account. In our case, no, because the assets that we have maps that are almost completely spread. But yes, I guess you could do that and remove those areas. You would get higher PSNR because you have less areas of the texture that you're trying to optimize for your MLP and your latent encode.
Okay, let's thank the speaker again. Yeah, the second paper is a collaborative texture filtering. The authors are Thomas Axne Moller and Pontus Evelyn and Mapfor and Bartur Bioronsky from NVIDIA.
Okay, so I'll start with a teaser, and here I'm showing a video of our algorithms. Our paper is about texture magnification, and we show it here for bilinear filtering with DLSS denoising. We have flip errors in the middle, where you should have as black image as possible. And I'll restart the video. And we have ground truth in the upper left corner, and then two algorithms that we've compared to. Our method is in the lower right corner, and as you can see, it has extremely low error. Nice thing about our technique is that it costs at most 1 texel per pixel, and often also 0 error. So before I start with the algorithms, I'll cover some background. What we call one-tap SDF in this presentation and in the paper is the filtering after shading work with stochastic texture filtering by far and others from last year. And the idea is very simple. Most of my examples will be with bilinear filtering. And so here we have 2x2 texels, and you have a sample point, let's say here. Then you can compute your bilinear filter weights as usual. And then SDF for stochastic texture filtering is simply stochastically selecting 1 texel, and you use the filter weights as probabilities. And you just choose that texel and use that as your result. This is a great paper, definitely recommended reading. And there's lots of good stuff about filtering after shading, which is really important stuff. So the second paper is what we call WaveCom SDF in my presentation here, and it's work by Bronsky and others from May, so it's very recent, and the idea there is to sample 1 texel using SDF, one-tap SDF, and then weight them together. So we have this estimator, which I won't go into the details about, but basically you gather texels from neighboring pixels, and we do that in an inexpensive way using wave intrinsics on the GPU. And what we get is good performance and increased quality because we get new texels from the neighboring pixels. Sometimes this can be a little bit wasteful because sometimes you gather or you produce the same texels or you fetch the same texels multiple times, which means that you don't get any new information. So we want to improve on that. And so primary motivation for our work is that recently a family of neural texture compression techniques have appeared, and those are kind of expensive, but usually high quality. And so our assumption is that we can afford at most 1 texel per pixel. So one-tap SDF and wave communication SDF are 2 solutions for that. But as you can see in the images here, we would like to get a little bit better quality than that. In fairness, I should say that those techniques are often used with some kind of denoising. So it could look a lot better than this, and I will show images of that later on. So before we dive into the algorithms, if I had been a really good researcher, I should have asked this question at the very start of our project, but it turned out that this was almost the last thing we did for our paper. So the question is, if you have bilinear filtering, how many unique texels are needed to achieve 0 error when you do the filtering? And it was quite surprising, and we don't have a proof for this. This is experimental. We did this by looking at a quad, texture quad at different rotations and magnification of 1. And quite surprising, you need less than or equal to 54 texels per wave if you have a 32-sized wave. And so that leads us to a question, what can you do with at most 1 texel per pixel? And it turns out you can do a lot with that. And that's what I'm going to talk about now. So our algorithms are called collaborative texture filtering. And as I said, the techniques, we have 3 techniques, and they produce a single texel per pixel. The rest comes from sharing within a wave, GPU wave, and we often have 0 error. We actually have 3 algorithms for this. The first one is called list merge. It's not very fast, so I won't talk about it much more, but it's interesting because it's the best possible solution in terms of how few texel evaluations you can get away with. Okay, so I'll talk about the basic algorithm flow for these techniques. And here I show with the toy example a GPU wave which is 8 lanes wide, configured as 2 by 4 pixels. And the first step is to have the lanes in the wave collaborate, so they find out exactly which texels are needed to get away with 0 error for your filter. And that gives you a unique texel set that this wave needs. Second step is to let each lane produce a texel. This could be neural decompression, for example, or whatever procedural texture generation, for example. And then in the third step, each lane gathers the texel it needs from the lanes in the wave. And as an example, I'm showing the lane 0 here. It needs the red, green, blue, and white. And then it's weighted together, and maybe you get a pink pixel. And that's, of course, done in parallel for all the waves. And I'm just showing one more wave, the last one. But here you can see that the blue texel is shared between those 2 lanes. All right, so we skipped the first algorithm. The second algorithm is called box sampling. So here we walk through the steps 1, 2, 3 that I showed on the previous slides. And the first step here is to compute an axis-aligned bounding box around the 2 by 2. So again, the example is bilinear filtering. So we compute a bounding box around the 2 by 2 texels that we need for each lane. And then we use these wave active min and max, which are wave-wide functions that you can use to get the minimum over the entire wave. And for step 2 and 3, we need an invertible mapping from lane index to texel coordinates. So this is simply, a mapping from a 1-dimensional coordinate to a 2-dimensional coordinate. And everyone has done this a million times if you're programming graphics. Here you need actually to subtract the upper left corner, but it's very simple. And as you can see, there are some gray pieces here as well. Those are actually not texels that we need, but we fetch them anyway in this algorithm. So the step 2 is to let each lane produce corresponding texel. So we use this mapping function that I told you about. So lane 0 produces texel 3.1, and so on. And when all lanes have produced their texels, we need to let each lane fetch the 2x2 texel it needs. So for example, for this pixel C, we need these 4 texels, and then we use the inverse mapping function. So for 2 maps to lane 5, so then we fetch that texel value by using a function called wave read lane at to get that texel value. And then we do that for all of those 4. And finally, we weight them together to get a 0 error result. So next, I'll show, I'll describe algorithm 3, which is a little bit better at exploiting or at doing useful work in all the lanes. So for example, if the texel grid is rotated, for example, 45 degrees compared to the pixel grid, then you can get lots of unused lanes in this method. But the next one, called mask sampling, doesn't do that. And it works like this. Step 1, we need to find out which texels are needed for 0 error filtering. We compute a box, as in box sampling. And then for each lane, we create a local 2D bit mask where we basically stamp out the 2x2 texels that are needed by the lane. And so for pixel A here, and again, we've subtracted the upper left corner. We just mark the 2x2 bits in the bit mask here. And then we can do a wave OR over these bit masks, and that gives us a bit mask which holds all the unique texels that are needed by this wave. So similar to box sampling, we need a mapping to go back and forth between the lane index and texel coordinates. And so we enumerate only the texel lanes that we actually need, or sorry, we enumerate only the lanes whose corresponding texels we need. And those are the ones inside the green area. This mapping function is a little bit more complex. So for lane to texel coordinates, we use a find and set bit. And the inverse is counting set bits on one side of the texel coordinate. In practice, we use an 11 by 11 bit mask using 2 unsigned int 64s. And then step 2 and 3 are done exactly as in box sampling, except that we use the mapping shown above here. So what happens when we are not able to produce 0 error? So it can happen that we cannot deliver 0 error with at most one texel evaluation per lane, and in those cases we resort to what we call fallback methods, and we still only use at most one texel per lane, but the quality becomes a little bit lower. And we have a basic method denoted by C, and what we do is that we let each lane produce a texel using one tap STF, and then we gather texels from 3x3 neighbors and weight them together using this function. And so the first part here is just a weighting of the gathered texels that we have. We might not get all the ones we need, and then we have an extra term that reduces error a bit. You have to look at the paper for the details. We have also an extended method called C+, and it's a bit similar, but it also exploits lanes that have no useful texels to evaluate. You have to look at the paper for the details. All right, I'll switch to results. I have some visual results for bilinear filtering. This is a very simple scene. In the red square, we have zoomed in on a region which has actually 0 error for our method, but the yellow one is a region, 32 by 32 pixel region, which has the most error with our method. And we have error metrics, PSNR, which should be as high as possible, flip should be low, color video VDP should be 10 at most. And then we have, so the first row is not denoised, and then it's denoised here. And you can see that we have really high quality with our method. And then we can also handle higher order filters, like, for example, bicubic Catmull-Rom filtering. And here is not denoised. And I should say that Wavecom STF does not handle negative weights, which Catmull-Rom has, so it cannot handle this case. And again, we have a quite high quality here for our method. And an important thing here is that one-tap STF actually needs 2 texels per pixel because of the fact that they use a technique called positivization. Our method uses less than or at most 1 texel per lane. Okay, so how often do we actually need the fallback methods? And this is for bilinear filtering again. Alternatively, you can ask the question, how often do we get 0 error? So we did this experiment where we had a quad again. We could change the rotation, which is x-axis, and we could change the magnification on the y-axis, which is shown on the y-axis. And so you want as little area as possible in this diagram. And some observation, box sampling is a little bit more rotationally sensitive than mask sampling because we have this peak here in the middle. And mask sampling and list merge are identical, which means that you cannot improve mask sampling anymore. The really important takeaway, though, is that you can see that box sampling above 2.35, you actually have 0 error always. And for mask sampling, this happens even earlier at 1.59. And that 1.59 means that a texel is enlarged to cover 1.59 pixels. So it's not a lot. Image quality, here you can see those factors again. At 1.59, the PSNR goes up to infinity, which means 0 error. And you can see that box sampling takes a little bit longer. And we also have, our methods have higher PSNR, even at low magnification factors, where we have this fallback method. Performance, I'm not going to talk a lot about this, but the results are shown in microseconds per megapixel. So in a sense, all of the methods are really fast. And in parentheses here, we have the fallback methods. And the second parenthesis is average over this magnification range. And you can see those, you can actually see that, at magnification factor close to 1.6, we get 0 error, and before that, the fallback method shows up, which is a little bit more expensive. But still, compared to a full frame, which take 4,700 microseconds, 8.4 is not that much. We did some neural texture compression experiments. This is a super brief evaluation. We downloaded the NTC SDK. I made sure that all pixels in a scene that were rendered were magnified at least 2.35. And when we tried with NTC, one NTC texel and one tap SDF, the result was 89 microseconds per megapixel. But then the result is quite noisy. With our method, we got 93 microseconds, so it's a little bit more expensive, but not that much. When we did 2x2 NTC texels, however, this is classic bilinear filtering, but done in software. It was a lot more expensive. But yeah, case 2 and 3 have exactly the same quality in this case. Okay, so we have another expensive decompressor example. This is DCT decompression, where we basically do an 8x8 matrix multiplication per component. So usually it works like this. We do the red components, then green, then blue. However, we can actually sometimes exploit this to get a performance increase sometimes. And it's because our algorithms can actually detect which lanes do not have any useful work that it needs to be doing. So in this toy example, let's assume that we only need 2 texels for lane 0 and 1. So normally we could decompress red, green, blue like this, but we could also do like a classical vertical to horizontal transformation, and then we assemble the RGBs, and the performance gain is the difference here. And we have seen up to 2.5 times in terms of speed up. So this is very preliminary, non-extensive results, but at least we have a proof of concept in place. So how do we make a good algorithm recommendation? Pareto diagrams are excellent at this, I think, if you want to find the most quality performance efficient methods. And I must say that I have not used them that many times myself, but I should have, and I will try to do that more in the future. So the Pareto, in this case, we have runtime cost on the x-axis, we have PSNR quality on the y-axis. So you want to be to the left on the x-axis, you want to be high on the y-axis. So therefore, the red curve here is a Pareto curve. So the recommendation is, in general, box sampling with our own fallbacks, and sometimes mask sampling can be the recommendation if you want to go after more performance, which we did, for example, in this DCT example. So conclusions and future work. Again, I mean, if I had been a good researcher, we might have been able to reach this point probably a year earlier. But research is seldom a straight path, and at least we got here in the end. I think we have addressed the shortcomings of stochastic texture filtering for magnification. And I'd like to think of our work as a clever per wave cache for magnification. We get 0 error above certain magnification factors with 1 pixel per lane. We handle bicubic filters with both negative and positive weights, and I'm not sure I ever want to look at bilinear filtering again, because those bicubic filters are really nice looking. Yeah, there's pseudocode in the supplemental for future work. We have some ideas, but we are already working on minification, and we have some initial results there. And I'll show you a video, and I'm thinking I'm out of time, but yeah, I can start taking questions maybe. But in this video, we have a ground truth filtered image in the upper left, we have magnification factor, and then we have the box sampling in the lower left and mask in the lower right. And the brown waves here are such that you need to call the fallback method. So the mask sampling doesn't need to do that very often. And then I'll just let the video run. And I guess I can take questions.
Okay, again, probably 2 questions.
Always, Carsten.
Sorry about that fascinating talk. Can you comment on when you have divergent control flow, right, in a path tracer, and you need to sample the texture? How do you deal with that? Do you switch into a, let's say, a serialization mode where you process only the active lanes and then use the full lane to do the textures, or how do you deal with that?
I'm not sure I understand.
So if you have a lot of divergent control flow, right?
Okay.
For example, in a path tracer, right? And somewhere you need to query the texture, right? How do you get the wave information back, essentially?
I'm not sure.
Okay, maybe take it offline, sorry.
Can we take it afterwards?
Yeah, sure.
Okay, sorry.
This work? Okay. Hello, great talk. I was wondering, so you mentioned this is sort of a local cache written in software. Do you have any insight into whether this affects the need for conventional, tiling formats inside the driver? Hardware specific formats? Could we get away with simpler or perhaps linearly laid out images in memory, because now we're taking care of the caching in software?
Yeah, I haven't thought about that either, actually. Yeah, sorry.
So the main benefits here are that you save on the sample cost, right?
Yeah, exactly. So we want to get away with, at most one texel evaluation or one texel decompressed per lane. And so what was the question after that?
So I was wondering, so in GPUs, they have these texture formats that are quite complicated instead of just having the pixels be linear in memory. And I was wondering whether that sort of obviates the need for that to a degree, and maybe you could have simpler texture formats that are more predictable.
Yeah, I don't know. I'm drawing a blank here. Sorry.
Okay, thanks.
Any more? Then I have one. So there are 3 ways of using that one. Then there's a fallback method. Then yeah, it's definitely bad for performance, and I would just pick the approximate one, so just using that filtering, even though that's not perfect.
Yeah, I mean, you can do that, of course, also. And we have evaluated that in the paper. I actually have some slides on that as well, but we show in the paper that we have higher quality than previous methods, even if we use only the fallback methods. So that, yeah, you can do that as well. But then you never get 0 error. Yeah.
Okay, thank you. Yeah, let's thank the speaker again.
Yeah, good. Thank
you. The last paper is GATE, Geometry-Aware Trained Encoding Hardware Accelerated Neural Block Texture Compression with Cooperative Vectors. The authors are Jakub Buksansky and Daniel Meister, Carson Benton from AMD, and Jakub's going to present the paper.
Thank you. Can you guys hear me? All right, so let's get started. I'm Jakub. We will be presenting our geometry-aware trained encoding. In this work, we have been looking at the problem of how to encode input into a neural network, specifically how to encode the position in 3D space for a neural network like an MLP, for, let's say, algorithm like a neural radiance caching. And I understand that not everybody is working with neural networks all the time, so I will do a little introduction to the problem that we are trying to solve. Let's start by thinking about why some kind of encoding is even needed. Let's say we have this little problem, like we have points in 2D space specified by 2 coordinates, and we want to train our neural network to classify them between red points and green points. So we can just put these 2 coordinates as input to the neural network as 2 neurons. It's not a very difficult problem. Even a small neural network will be able to learn it quite fast, but with a suitable encoding or mapping or transformation of these 2 inputs, we can make a job for the neural network much easier. So in this case, let's imagine there is some center point in the middle of these red points, and we apply a transformation to these 2 coordinates. We introduce a 3rd coordinate, which is a distance from the center, and we will plot it on the chart on the right, and now we will see that actually classifying these points into 2 groups is absolutely trivial. You don't even need an MLP to do this. It's just a comparison based on this decision surface. This is commonly called the kernel trick, although the real kernel trick is much more involved. But I think it's a very good example why transformation, even a very cheap one, can make the neural solution much more efficient. So let's take it closer to the practical solutions. So previously, each of you could stare at the problem for a minute and figure out the best possible transformation to do it. Well, in practice, that's not so easy, and finding a good encoding function might be very tedious. It might be impossible. Such function might not even exist. So people started to use what's referred to as learnable parameters or trainable parameters. The way this works is, let's first define our encoding function as a mapping from our input space to some higher dimensional other space that can be a variable, and we implement it as a lookup table. And entries in this lookup table, they're essentially defining our mapping, and we can train it together with the network, specifically using the backpropagation. If you look at the diagram over here, you can see we have some lookup table, which is actually a grid, and then you get your input parameters, and then you put it to MLP. So the way backpropagation works, it propagates the error back through the network to your lookup table, and you can actually train it together. So automatically, you will get some mapping, which is optimal. It's not guaranteed to be the best possible, but it will work. What I found the best about this is that you can change your network, you can change your problem, and you don't need to think about encoding functions because they're automatically trained. So in this specific example, this image is borrowed from neural texture block compression. So as I said, the basic idea is to store these trained feature vectors in some grid or a lookup table. They give you mapping to higher dimensional domain. And you can also have multiple of these tables with different resolutions, different settings. For example, on this image, we have two grids. One is smaller, one is higher. You just encode your input point using both. You concatenate the resulting vectors, and you use that as an input to the MLP. So let's now get to what is the state of the art in this currently. I believe it's the multi-resolution hash encoding introduced a few years ago. We just call it HashGrid for short. And it's exactly what I described on the previous slide. It's like you have a grid overlaid your input domain. You can have multiple resolutions of these grids. What the HashGrid adds is a hashing, so to reduce storage and also possibly increase the efficiency and quality. Instead of storing all the feature vectors, you map them into a hash table. So what are the problems of these implementations? One is that you get interpolation artifacts. Of course, the grids are discretized, and let's say you want to encode a triangle in a 3D grid. Basically, every time you query your grid for every triangle, you get some interpolated result from nearest vertices of the grid. So it's never trained properly for your specific point in space. With the hashing, you also get hashing artifacts due to hash conflicts. If you use it for neural radiance caching, for example, these exhibit as weird colors, weird blobs, black blobs, or blurriness where you don't expect it. A pretty big problem is that you get scattered memory accesses because the grid is hashed. For 3D space, you need to load 8 vertices from completely different memory locations due to hashing. So you get perfect incoherency in your cache accesses. And the last problem is that the input domain is limited. Being a finite grid, you need to put it somewhere, usually stretch it to the whole scene using a scene bounding box. But what do you do when you do not have a bounding box on open-ended worlds or these games which just stream the geometry in and out? Scene box can change all the time, so this is a problem. And of course, if you're not querying your network in empty space, you are wasting storage to represent empty space which you're not using. So finally, let's get to our solution, which is a very, very simple idea. So instead of storing these feature vectors in a grid, let's just store them directly on the geometry, on the surfaces. So I will talk on the next slide how we distribute those feature vectors using mesh colors. For now, let's look at what advantages can this idea give us. So suddenly, the cache incoherency is gone because we don't use hashing. We have cache-friendly query, assuming your meshes are optimized for cache coherency. You can follow the same layout as you use for your index buffer, and you get nice cache-friendly accesses. There are no hash collisions, and interpolation only happens on the surface of your triangle, not within a volume of a grid. This is a big advantage because maybe for the hash grid you will have multiple triangles within the same cell, and then suddenly the hash grid needs to be trained for maybe completely different triangles. This cannot happen with our solution. We do not need a bounding box because you have your geometry. You can decide where to put your feature vectors, maybe all of your geometry or maybe just a part of it. And this essentially also deals with the teapot in the stadium problem. Let's say you have a huge scene, but you only render small parts somewhere. With the hash grid, you would have to do some tweaking, magic, bounding box skewing to make it work. With our solution, you just have your feature vectors where your geometry is. Thanks to all what I said, we get higher performance. I will get back to this. And now, disadvantages, of course, you need more storage, possibly a lot more storage. It depends on how much geometry you have. And it's only limited to surfaces, so you cannot query it in empty space. Maybe you have some algorithm which can be used in empty space, like some shadows, light sampling, these things. With our solution, that is not possible. And finally, we can only encode 3D positions, like I said, over triangles. Those hash grids, they can be used in 1D, 2D, 3D, maybe 4D if you do some magic. Ours is just 3D positions on triangles. So let's give you a little teaser of what results we get. So on top we have the example of neural ambient occlusion. So very simple, we just train neural network to do AO. And with the hash grid, which is stretched over this relatively large scene, you get a lot of blurriness in this case. And with our gate approach, we essentially get a very good solution. Like I said, this is solving the teapot in the stadium problem. Now on the bottom image, we have a neural radiance cache. I have to tell you, this is queried on the primary vertex to show you what it looks like. That's not how NRC should be used. You will do few bounces of light and then you will query the cache. But that will give us noisy results which are hard to read. I just find this like much easier to mentally parse the image, like what you see. So some imperfections are expected. I'd like to point out these tiles on the back wall with the violet light. So even in the small scene like this, where you don't have the teapot in the stadium problem, the hash grid cannot represent those tiles on the wall. They just basically completely disappear, including the violet light, which should be on them, while our solution works with these two. So let's now talk about how we store these feature vectors. We use a mesh colors algorithm from EGSR and France. If you're not familiar with it, it's very elegant, simple idea. We just want to distribute more samples over the surfaces of triangles and over the edges. And these can be shared, so the encoding is seamless over edges. It is controlled by a parameter called the resolution. We have image of 3 different resolutions. So the second smallest one is just adding 1 sample per edge, and then higher ones also add some on the surface. It's a very elegant algorithm. All you need to do is to decide what resolution you want to use for your triangle or the whole mesh, and you query it by triangle ID plus barycentrics. The algorithm gives you indices of those samples and their interpolation weights. So very simple algorithm. The code is actually simpler than the hash grid. And you can hierarchically stack these. It's the same as with the hash grid, where you have multiple resolutions. You can do this with ours as well. In our tests, we have used 2 resolutions. One was per vertex, so R equal to 1. And then we had adaptive resolution. So we figured out pretty quickly that using 1 resolution for the whole scene doesn't work. You can see this on the left. It takes 75 megabytes, and it's not very well distributed. We want to use roughly the same size, these little patches. So we have a simple solution which figures out your resolution per instance. Not only we achieve kind of equal-sized patches of mesh colors, we have also managed to reduce memory consumption with this. So why don't we go one step further and have per triangle mesh color resolution? Just quickly mention that it's difficult because then you have a mismatched number of samples over shared edges, and you have to do some magic to interpolate them correctly. We didn't want to go through this for this paper, but it can be done, of course. Now let's talk about how we train this. As I said, the idea is super simple. Instead of the grid, store it on the geometry, but it enables us to do some very nice things. We have used Adam Optimizer to train our network. And so my next point is only train updated feature vectors. So first I have to tell you how the hash grid implementation we used work. So the hash grid in typical setting has like 1 million entries. So you can actually execute the dispatch call to work on each entry with a single thread, and you apply Adam Optimizer on each entry of a hash grid. The original paper even suggests you can skip training the entry if gradient is 0. They get some 10% increase in performance, I think. Well, technically for Adam, you should never do that because the point of Adam is the momentum. So when the gradient is 0, it can be stuck in a local minimum, and Adam is designed to get it out. So even if the gradient is 0, you should apply the training. So with our solution, we can do this perfectly. We only run Adam on triangles that have been actually trained, which were assigned a training sample. And it's actually must for our implementation because we cannot run a dispatch call big enough to cover all of the feature vectors over all of the geometry. That would be too much. So we have a site buffer where we store where have been the training samples assigned, and we only train those. And that enables us to do what we call per triangle learning rate. So if you know how Adam works, it has some parameters called beta, which are updated after every training iteration based on number of training iteration applied to the vector you are trying to train. And with the hash grid, you have to use global number of training steps, but you're not training all the grid cells all the time. But with our solution, you can track actually how many times was each triangle trained, and you can apply this properly. So we achieve continuous training with momentum using Adam for each vector. So how do we generate the training data? With the solution I described so far, you can do some nice things here as well. So when you know how many times has each triangle been already trained, you can use this to do importance sampling and generate training data on undertrained triangles with preference. So the way we do this is, let's say we're generating some screen space samples, just deciding where to put our training data in screen space by sampling the G buffer. We can, for each pixel or each training example, we can pick 16 candidates, read how many times they have been trained, and run some importance sampling loop to select one with higher preference. And you can do the same for world space samples. You just sample the index buffer, pick some triangles, and do the same. Now, with generating training examples in world space, I didn't get super great results with that because if you think about just this scene, there would be training examples generated behind the cupboard, basically in unreachable areas of the scene. So I think this could be some good idea for future work, just detect which areas are not reachable and you don't need to train them. And these images actually demonstrate difference between using importance sampling or not. So if you notice in the red circle on the top, there are some very tiny triangles in the creases between the tiles on the wall, and they are undertrained after 32 iterations, and it exhibits as some kind of glow. And with our fix, using same 32 iterations, it's much, much better. It's still visible, but it's converging much more quickly. So let's get to the results. We have used this for 2 different algorithms, neural ambient occlusion, super simple thing. We have used the feature vector of length 2. So that's our input encoding does the encoding from 3D space to 2D space, so it's not actually embedding to higher dimensional space, but lower. For NRC, we found we need to have more features per feature vector, so the length is 8. As I said, we only query it on primary hits. And an important difference between our original implementation of NRC and ours is that for the hash grid, the original implementation uses a lot more inputs. There's a scatter direction, normal, roughness, and some reflectances. And I believe in my mind, it's designed to kind of help neural network identify which surface you're querying, because as I said, every voxel in this hash grid can be straddled by many triangles. So this is additional information that helps the NRC algorithm with hash grid do better. But it complicates the problem, right? And for gate, we do not need to do that because each feature vector is bound to every triangle. So we use less inputs for gates, and we actually get better results with these less inputs. Because when we add these inputs, it's shown on the left, we get some color fringes, simply because the problem is more difficult to train, to learn. And as I said, we use 2 stacked resolutions. That's less than for the hash grid. For the hash grid, we use 8 resolutions. With gate, we can only do 2. That's another point where our performance increase comes from, and we still get the better quality. So this is a few results on the neural amid occlusion of hash grid versus gate. The best result we get for the Vespa in Bistro, which is the teapot in the stadium problem, which was kind of what we designed for. But we do get lower flip error for every scene, even the small ones. Now let's look at the radiance caching, a more difficult problem. It's basically very similar results, but I'll point out to the last row where we do get worse flip error with our gate. Just slightly, but it's there. But I would point out to you, again, those tiles with the violet light, they're missing from the hash grid. So even if the flip error is almost the same, there are missing features that cannot be measured with flip, I guess. So in terms of performance, we have done several comparisons. You don't need to read the whole table. I think the most relevant for practice is comparison of the first row, which is gate hours, and the last row, which is hash grid small. It's not apples to apples comparison because hash grid is using much, much less memory, but it's how I would use it in production. So I guess that's fair comparison. If you want to look at equal memory comparison, it's the first 2 rows, hash grid large and hours. But those are hugely in favor for us. The training performance is very, very slow for the hash grid. And it's because we use that implementation which executes the compute dispatch over all of the entries. So, but the bottom line is that we still get about 1.7 to 2.7 faster inference with our solution. It's because we have coherent memory accesses, simpler code, and we have simpler network possibly with less inputs. Like I said, flip metrics is always better for gate, except for that one example, even regardless of the hash grid size. So let's talk about training speed. And here I don't mean training speed as in the clocks or time, but in terms of training iterations. You can see that after 16 iterations, our gate is already looking pretty good, while the hash grid is still learning. But the most important thing on this image is the chart. The orange line is the hash grid, and you can see that it plateaus pretty quickly, and then it just becomes horizontal. It doesn't get better with more training, while our solution gets progressively better because it's adapting to the geometry of this scene. So we're almost done. Let's now take a look at some videos. First videos, a neural radiance cache in Bistro for the primary vertex. And this has not been pre-trained. This is trained in runtime as I started the application from frame 0. You can notice how it trains on the disocclusions. Now it will do a turn, and you will see some training in runtime. I should have told you that I also removed the color the textures so that we can see this better. So next video is the same thing, but in comparison to the hash grid. It's side by side. So hash grid flickers somehow. And of course, this is bad example for the hash grid because it's this teapot in the stadium problem. I have another video later which is more fair in terms of scene size. Okay, so next video is ambient occlusion in interior. I will tell you that the camera will fly around and then it will cross the door. It will enter the train. And that demonstrates how our per triangle learning rate actually works, because then it suddenly sees stuff it has not seen before. It sees it for the first time, and because of this per triangle learning rate, the learning rate will be very high for these newly seen triangles, and it will adapt very quickly. So let's see that. 3, 2, 1. Yep. And once more, again, the same thing, comparison to hash grid. Okay, and the last video is the neural radiance cache again on a very small scene where actually both approaches are using equally same memory as out of the box without any tweaking. I want to show you this specular highlight on the floor. The camera will move around and the specular highlight will follow. So I want to demonstrate that our method works dynamically for dynamic scenes, even the specular highlights. But I needed to increase the learning rate to double the usual amount, so it will flicker elsewhere. So let's just see it. So again, far from perfect, but works. And there's some flicker on this wall behind. So see it once more with the hash grid. Okay. And since this is kind of neural paper where ablation studies are standard, which I like, let's very briefly talk about stuff that didn't work. I said that lowest resolution we use is per vertex. We have tried to go one resolution lower to go per triangle, but that revealed discontinuities between triangles. So it was not worth it. Mesh colors without edge sharing, again, discontinuities, that's useless. You have to go through pain to implement that. Using only single mesh color resolution, that was very bad for training. And learning the interpolation, this is the idea borrowed from the neural texture compression paper, where we would not interpolate these 3 nearest feature vectors. We will just throw them into MLP, concatenate it, and we would hope that MLP would learn to interpolate these vectors in the best way. Well, turns out the best way is the linear interpolation almost always, and it just takes ages to learn, so that didn't work. So the summary, we achieve better performance. We can do nice things like per triangle learning rate and adaptive training data generation. We have simpler MLP because the less inputs. We remove the problem of normalization of input to the scene bounds, but we do require a lot more storage, and we are limited to 3D positions on the geometry. So for the future work, we want to do what we call the clustering. For very finely tessellated geometry, even the per vertex feature vectors are too much, so we want to do per cluster. Don't know how yet, but it needs to be done. We want to do some adaptive mesh colors allocation to the scene. I think it would be nice to say we have a fixed budget of 100 megs for this, just distribute my feature vectors in the scene where they will be useful. I don't want to do this myself, but maybe someone can try a different mesh parameterization, like a PTEX. I like mesh colors. Some people hate them, so go figure it out how to do it without them, I guess. And we want to do pre-training. We can think of the MLP as a decoder for some fixed representation that would solve a few problems you can read on in the paper. So I thank you for your attention, and let's hear your questions. Thank you.
So we are behind the schedule, so just 2 questions.
Hi, thanks, nice talk. You were mentioning the teapot in the stadium problem multiple times, and this problem comes with two sides. Like, you have a large scene, but you're only focusing, and everything which is important to your image is only like one small thing, like you zoom in on the teapot, meaning that everything else around the scene is more or less not important for you. So, and usually the problem with these fixed resolution grids is, yes, you have a huge grids, meaning you have large cells. But the other side is, if you make a high resolution grid, you just waste a lot of memory. And now it seems you went from the one side to the other, because if your solution is now to tessellate the scene and make all these small MLPs at each cell, then you probably waste a lot of memory for stuff you will never touch, and it's not impossible. I think you mentioned it a little bit in the end with the adaptive coloring.
Yeah.
So have you thought about some sort of adaptive tessellation and then distribute it afterwards?
Yeah, so this is all future work, and you are absolutely right that we just for many scenes we cannot allocate for all the geometry, and you have to somehow figure out which parts are needed. So yeah, that is just the future work. The biggest limitation of this, what I presented now. So, yeah.
Because for hash grid, you would probably try something like cascaded hash grids, which overlay and.
Yeah, or you can just repeat the hash grid, just hash it to the same locations. That's also possible. You can do it.
Okay, thanks.
Any more?
Really good work. Really
Thank
good
you.
Presentation. Very interesting. You touched on a few things, like magnification and dealing with high vertex density, and magnification, and when you interpolate between values and so on, right? And looks like some of these problems are also the problems that Nanite, for example,
Nanite, yes.
tackles, right? So I was curious, have you tested on anything like Nanite, where you have clusters and more unified geometry density?
No, but this kitchen scene is a little bit like Nanite style, where you have many tiny triangles on the wall. It takes 75 megabytes if you do single mesh color resolution for the whole scene. And then when you just assign lowest resolution just for these triangles, the memory consumption goes down to 20 megabytes, so 4 times almost. And the quality actually goes up, because if you have these tiny triangles still tessellated more, you are only training one tiny little patch of subpixel size. That needs to be solved. That's like the biggest problem, what I see with our method right now.
Thank you.
Okay, the last comment is, please return to your best paper ballot to this box. Yeah. And let's thank the speaker again.
Thank you. Oh, you forgot your food. Thank you.
How do I know whether it's muted? It's on the screen. Oh. So.
Is this on? This is on.
somewhere in front, and because I say the last words here about the keynotes and the acknowledgements, and then I say, and one more thing before the keynote, and then you, and then Johannes announces Andrea.
All right, guys. We were actually planning to open EGSR in the break, but there was a little bit too much commotion maybe. So now we will do it first and then go on with the keynote after that. So welcome to everyone who wasn't here for HPG and just came in today and picked up an EGSR badge, and welcome to everyone here that are here for both conferences as well. So we will go on with the 36th version of Eurographics Symposium on Rendering. And can I ask you to switch the slide? So here's just the conference at a glance. As you can see, we are a little bit behind, but this means that you might lose 15 minutes of your lunch break today. But today we have a shared keynote with HPG, and in the afternoon some paper sessions. If you are here for HPG, you can stick around if you want and see some of the EGSR paper sessions later in the day. Tomorrow we have a keynote in the morning and a paper session, and then we have 2 sessions in the afternoon, and then we have this excursion to an old brewery in Copenhagen called Carlsberg. It's not the present brewery today, so it's more like a historical tour where they made an audiovisual exhibition. And then there will be dinner in the same place afterwards. And the third day is with a keynote in the morning as well, and a paper session before that, and then 2 paper sessions in the afternoon, and then we close with a best paper award. So, yes. Just a great thanks to the program chairs who will take over in a minute, and to the program committee as well. We have 180 people signed up for the conference, so I think that's very nice. And also thanks to our event supporter Natasha, who's you might see her outside at the registration desk from time to time. Yes. And of course, also we want to say a big thank you to our sponsors, without whom we would just be in an auditorium without much to drink and without any events after these academic sessions. So a very big thank you to the sponsors of EGSR 2025. And then I will pass the mic on to Alex.
So, hello. My name's Alexander Wilke, and together with Bebe Wang, we were the paper chairs of EGSR, those responsible for curating and shepherding the academic program that's the core of the conference. And since we're behind, we won't take much of your time. The core of the effort, apart from those who submitted their work, were the 70 members of the IPC. You can see the statistics there, and just writing a line there doesn't do it full justice. We can't really say enough thank you to those who volunteered to be on the IPC, because it's unpaid work and it's actually quite complex work. And if you compare that with industry, I mean, if I think about what I charge for 1 hour of consulting work and you did all that for free, 4 reviews per paper, 70 people, think of the amount of value that you missed, so to speak, if you think in the categories of our modern world where everything needs to have value. You did a great job contributing to the academic community. Thank you so much. It wouldn't work without you guys. As you can see, it's quite healthily split between industry and academia, and the statistics also speak for themselves where the current focus of graphics research in industry is. As for the review process, we're going to have the town hall, so where we can have a discussion at the EGSR town hall later today. But for once, I hope we can bury the topic that EGSR is dying, because there was a healthy number of submissions, although there was a large number of desk rejects for simply being completely off topic or breaking the review conditions, like not being anonymous. But still, a huge thank you to the community too for actually making EGSR more alive than it used to be. And we also had 2 industrial paper submissions. We actually had 3. So this is a warning for next year for anybody wanting to do this. A third person submitted a paper and it got killed in their mail server in the company as an outgoing PDF, and it never reached us. And they only started complaining when they never heard back way after the deadline. So at least there is an industrial paper program this time.
And in the next, let's look at these curves. So compared to the last 5 years, this year we have a significant increase for the submission numbers from 50 to 83. And then let's look at the distribution of the authors. So about 1/3 come from China, followed by US, Germany, France, Switzerland, and etc. So this year we are going to have 8 sessions that consist of the 48 presentations. So there are 45 accepted research papers, 1 industrial paper, and 2 CGF presentations. And here is our program, which is obviously very long. Okay.
Yeah, so we're going to have 3 great keynotes. Of course, Andrea coming up next. Then there's towards physically and socially plausible 3D generation tomorrow, and a bit of an oddball, but an interesting oddball on Friday from an art historian who uses computer graphics to figure out things about paintings. That's going to be looking at computer graphics from the other side, so to speak. And as for acknowledgements, Stefanie Behnke is a name a lot of you probably will not have heard. She's the admin, the chief admin at Eurographics, and without her nothing would work, because she's the one who holds down the whole paper submission and review system with an iron thumb, and whenever something goes wrong, you email her, and at 3 in the morning she still answers. So without Stefanie, nothing here would have happened. Then, of course, a huge thank to Jeppe for being the local organizer, because that's an enormous amount of work, speaking as somebody who did it previously. To George, the steering committee, for keeping EGSR alive all these years, because that's no mean effort, just working behind the scenes, keeping the conference consistent over the years. The program chairs, the IPC members, the session chairs, thank you, all those of you on whom we dropped these tasks at comparatively short notice. And then, of course, an anonymous thank you to the Best Paper Committee, because we picked some senior people who will be going around and watching presentations and, in a rather undemocratic but very academic way, figuring out who to give the NVIDIA prize to afterwards. All right, before we move to the keynote, one more announcement for an event tonight.
Thank you. Just quickly, we have an event tonight for women in rendering, but of course it's open to everyone to join. It's for building network and just chat and enjoy a fancy dinner. You must have received an email. Please RSVP if you're interested, and hope to see you all.
And of course, there is also a welcome reception from 5:30 to 6:30 after the scientific program.
All right, welcome to today's keynote. This is a special one because we have this tradition at HPG and EGSR to organize a joint keynote. And so it is my honor to introduce this year's joint keynote speaker, Andrea Weidlich. Andrea's work has a strong focus on appearance and materials. She has published on the rendering of gemstones, rendering with polarized light, fluorescence, yarns and cloth, feathers, spectral rendering, layered materials, and the list just goes on. During her time at Weta Digital, Andrea designed the material system for Manuka, which is Weta's production renderer. And her long list of film credits include The Hobbit, Battle of the Five Armies, War for the Planet of the Apes, Avatar 2, and many more. Andrea is now a principal researcher at NVIDIA, where she continues her work on appearance models and spectral rendering. Today, Andrea will share her thoughts on how neural materials can peacefully coexist with analytical approaches. Please welcome to the stage, Andrea Weidlich.
Well, thank you very much for the introduction. So there are two things I would like to say before we start with the talk. And the first one is, what I'm saying, those are my own words. They do not reflect, of course, the opinions of any former or current employer. And the other thing is that I know that some people can react not in a good way to AI or diffusion-generated content. So any image which was generated by these means, it's marked with a star in the right top corner. But let's start with materials, because as Johannes said, I am a material person. I did my entire academic life, I did materials. I've never done anything else. It's quite a focused thing, but then I did everything with materials. And these days, it's kind of a good time to be a material researcher, because a lot of people these days are doing material research, and there is a strong focus on how to get materials more realistic. And in particular, these days, you can read quite often in publications things about high-quality assets and photorealistic materials. This is something we have used in the last 20 years quite often. Film-quality assets, film-quality materials is another thing. And as a person who worked in production for many, many years, who worked on a production renderer, these things, they're something which are very dear to my heart. And so as a start, I would like to share what it means to produce film quality assets, film quality materials. Because what we do see as the gold standard these days, it's materials, it's visuals from feature films. And the reason for this is because feature films, they aim to produce graphics which is indistinguishable from reality. So this is what we want to achieve. We want to have something which is not just plausible, which really and absolutely fools you in a way that you think it is real. The way it is achieved in VFX is with long iteration times, with a lot of compute and attention to detail. And normally, when I would ask someone, what do you think is a difficult material? What people would normally say probably is skin, and then followed by hair. And yes, this is absolutely correct. Both skin and hair are super complicated. But as a matter of fact, we spend a lot of time with both to get them in a state where they look really, really good. So less obvious, it's all the other materials which are there, which are the environment materials. And we have so many more materials we need to be able to describe, and which are actually very, very hard to describe. So if we have materials like fabrics or stones, vegetation, they have all a very complicated internal structure. Like there are fibers, there are multi-layered materials, there is porosity. It's really hard to capture that kind of appearance. And in fact, even offline rendering, what we think they have figured it out, no, they haven't. Even the VFX industry, for them, it's a lot of trial and error to get the material right. When I say getting a material right, it's always the question, what makes a material look good? When does it look good, and when does it look CG? And materials, real materials, they have some kind of, I mean, you know, if it's good or if it's not good. You just implicitly know. So what we have is material complexity. Real materials are a complex thing. They have a variety of different effects. They will have micro sketches and small vents. They will have signs of wear and tear. There is variation, but the most important thing, this variation, it's not an arbitrary variation which is anywhere. It is done on purpose. The other thing that is there is never a sharp edge on an asset. What I mean with that is the sharp edge is the equivalent of the perfectly specular BSDF. It does not exist in reality because a Dirac impulse is something artificial. Sharp edges and round edges, they will produce a different kind of visual appearance. The round edges will do something different to the highlight, and the human eye is trained on seeing that and not the sharp one. Then we also have a lot of details in real materials. Details like dust or manufactured artifacts, very, very small details which you do not immediately see, but you still perceive them. And the way to do those would be with a high texture resolution. In particular, visual effects industry uses an insane amount of textures when it comes to building materials. The tool which is normally used to achieve this is called UDIMs. I've noticed that people from the games industry or academia normally do not come in contact with UDIMs. UDIMs is a way how you can split your asset, your object, into multiple different texture regions so that you can increase the texture resolution. Let's have a look now at how this particular T-bot is built up. Assets, materials, they are built like real objects. So you start with the clay as a base material. The clay will have some kind of normal map, which is a little bit hard to see on this projection, but believe me, it's there, totally. And then you put some kind of absorption layer on top of the clay. The absorption will cause a few dependency in the absorption so that it becomes more saturated at grazing angles. It's driven with a thickness map, so another texture, and then you put the clear coat on top to have your base ceramic. The clear coat, it's 2 dielectrics, not 1, so that you have more roughness variation in there, that you can do something like fingerprints, like stains, like smudges, something which gives you more visual fidelity. Then on top, we do then have something we call the imperfections. You will have water stains on top, like the smudges, something like diffuse BRDF, which is half see-through so that it roughens the dielectric below, and a couple of dust flakes because everything is somehow dusty and you also want to have those. So those dust flakes, they're super, super tiny and you wouldn't even see them normally if you don't look carefully. All the textures which are used here, and you can see it at the side from the individual BSDF layers. Every single of those squares represents a texture. So all of them are 4K textures, and the asset has 14 UDIMs. This means that every textured parameter has 14 4K textures which are on the asset, which is a lot. So these details we are seeing here, they are not arbitrary. It's not that people just put them there randomly and then they are there. No, they are there for a purpose because they need to tell a story. And it is sometimes harder to not do all these dirt and imperfections than to do it. It's always a question of how aggressive is it in the end. And so the key word is well-loved and not necessarily dirty. For reference, so those stats, I took them from a paper because it's really hard to get production stats. The stats are from a 2018 paper, and you can see that I'm not making this up. In a classic scene and a classic frame, there are a lot of textures, there is a lot of complexity going on, and this is what we need to achieve. Materials, again, they are there to tell a story. We don't make them as complicated as possible just because we can. They need to serve a purpose. And this complicated thing, this is our means to adjust the materials. I really like to, when I talk about materials, to bring this example of why it is important to have this material complexity. Skin, how we would normally see it, like you have some kind of epidermis, which is the outer shell of the skin, and then you have some subsurface scattering, bulk medium, and that's your skin, and this is normally the skin we do in academia, in research, and it's great, it looks like skin, but it looks like the skin of a newborn baby, it looks like the skin of someone who have never seen anything. Skin, in reality, is not like this, because everyone has scars, everyone has bruises, tattoos, all these things. And just by changing the appearance of an object, of a character, you can give something a background. You can ground the object in reality, and you can give it a history. Depending on what you do with the appearance, you know if your character just exercised because it's sweaty or had an accident because it's bloody. So all these things, they play together and are very important. Making production materials, it's not about making them as complicated as possible. It's also not making them as physically accurate as possible. It's always a mixture of different requirements. And in particular, in production, you need to have the sweet spot between performance, artistic freedom, and correctness. Because you still need to be fast enough to evaluate your frames, you need to be correct enough that it looks plausible, and you need to be flexible enough to give an artist the capabilities of expressing themselves the way they want. Today's material systems, they are almost exclusively layered material systems, like layering of BSDFs on top of each other, like I showed in the beginning. So why layering? Mainly, it's a convenient thing. It's a convenient thing of creating appearances, of creating materials. It's a natural way of modeling because it reflects our realistic workflows. You can build templates with the layers, but even more important, it's a non-destructive way of material design. It's because you can't adjust it with masks, you will never have your final material all in one. It's a different thing than having an Uber shader where you would bake all your material properties into specific texture maps. Layering operators are the cornerstone of a layered material system. We have classic operators like mixing and coating as a combination. There are a lot more, some more esoteric than others. Recently, there's also a lot of thick code going on, which is taking proper refraction into account, bouncing between layers, but it's more like an exotic operation, which is not very popular. What we do is say, though, when we have a layering system, we can decide, we can differ between horizontal layering operations and vertical layering operations. Horizontal, where you do not increase the size of your stack, and the verticals, where you do. What we fill the layered material system with are BSDFs. And depending on your material system, you can have a couple of them, or you can have a lot, like I did in Manuka. I did a rough head count in 2019, and I counted 172 different BSDFs and phase functions. This is a lot. 67 of those were really unique BSDFs. And by unique, I mean unique source code, unique appearance, standalone BSDFs, which would not have anything in common with other BSDFs. Of those 67, we had 54 surface BSDF, BTDF, BRDF, and then 6 fiber BCSDFs, 5 phase functions, and only 2 emissive EDFs. What we can see here is that we are a lot more concerned with the reflectance of materials of objects than with emission, because apparently no one cares about emission. 67 is still a lot. It's not as much as 172, but still a lot. In practice, it's not that you use all those 67 all the time. You have a core set of BSDFs, which you would use, and most of you probably here have seen those BSDFs I showed here. Those are the core BSDFs. It's a surprisingly small set, and it's absolutely not the latest and greatest in research. You can see that they have some time on it, especially the Lambert one. What they give us the sweet spot between usability and expressiveness. And much more important for production, they are battle-proven. It means that we exactly know what they do, we know how they behave, we know their performance. They are just our best friends. These canonical BSDFs, they are part of most, or actually I think all material systems. They will be in Material X. Material X is a layered material standard in the VFX industry. You will have them in Llama, you will have them in Unreal Substrate. It is the canonical set of BSDFs. Additionally recommended, I would give a glossy, unrefracted transmission so that you can simulate something like diffusion through a thin material. View-dependent absorption, also very, very nice to have. A good fabric material is also something you cannot say no to because that's the things these materials cannot do. Where material systems differ, that's the part where you have the crosstalk between the BSDFs. Because you can say, well, in its most simplest form, the BSDF is a standalone object. It's kind of black box. It doesn't know anything which is going around itself. But in modern layering systems, modern material systems, BSDFs, they will change their appearance depending on where they are in the stack of the materials. And in particular, we have two important operations, IOR accumulation and roughness accumulation. IOR accumulation means that the BSDF will change its reflectance based on where it is. So in this simple example, two dielectrics coated on top of each other, same index of refraction, which means they are index matching. The second one should, in theory, completely lose its reflectance. Without IOR accumulation, you can see two highlights. That's clearly wrong. With IOR accumulation, the second highlight vanishes. And similarly, roughness accumulation. The theory is that a material can never be smoother than the material on top. So you need to have the roughness transferred from the top to the bottom. And same game, the bottom highlight should be rougher than it is. It should not be specular, but it is. But with roughness accumulation, this is gone. More like a requirement, not a fancy thing to have, is how you decide which transmission you would have. This can become complicated if you have a couple of transmissive TDFs on top of each other. Which one do you use for the transmission? Do you take the bottom one because it was the last one in the stack? Then you would get the perfectly sharp refraction here. Or would you take the roughest one? So that's the first one. Or do you take a combination of both? It's really not easy to decide because this is not a physical process we are emulating here. It's up for the design of the material system and the artist to decide what to do. I mean, in production, it's kind of easy to say what is correct because correct is always what the client wants. It's not about physics. It's not about what you want. It's about what the client wants and what the client expects. These examples, they look super easy and easy to decide what to do in the simple case. Believe me, once you get materials like I had with the teapots, it can become very, very complicated what to do. Key is an efficient computation, so what you do not want to have is combinational explosion, and you don't want to have a noise from stochastic processes. Okay, if we now compare this layering to the classic PBR material we have in academia and we would have in real time in games engines, for example, we can see that the PBR materials, the PBR BSDFs, they are a subset of the layered BSDFs and a subset of the layering what we do. They have the same components, the same canonical BSDFs most of the time, but they have a hard-coded order of how the BSDFs are ordered. And they are good at some things. I mean, we wouldn't use them if they would be bad. They are great at doing ceramics, at paint, hard plastic, rust, concrete. So a lot of materials actually, but they're really, really bad when it comes to more complicated materials like multi-layering, like fabrics, like, like porosity, all these things. They cannot be done with the simple PBR materials. And where things really, really start to break down is at grazing angles. It's very hard to get grazing angles right with a simple PBR material. So PBR materials, great, but they don't give us the fidelity we want if we expect the fidelity from visual effects. So when can we expect that real-time rendering catches up with the appearance of offline rendering? Generally speaking, there is a flow from, okay, you start with academia, you research something, and then you go to offline rendering, and then you go to real-time rendering. So there's a flow of technology until something becomes practical. And we have, for example, if we look at path tracing started in 1986. And if I look into this room, there are probably a lot of people here who were not born in 1986. It took 20 years until we had the first path-traced feature film. So generally speaking, normally people say the first one is Cloudy with a Chance of Meatballs. And it took almost 20 more years until we had the first path-traced AAA game. For layering, it's not as simple to pin down because we don't have the seminal paper which we're introducing arbitrary layered surface combinations. We have a couple of them which we can say, okay, they were the beginning in the 1990s approximately, like Pat Henrehan's paper here. Again, it took more than 20 years before we had a feature film which was using an arbitrary layered material system in a featured film. And even now we don't have a game, a AAA game, which is using layered material systems. Although we are close. With Unreal's substrate implementation, we are close to having the first multi-layered material system in a game. The reason why technology transfer works is because algorithms, they become better, but more importantly, hardware becomes faster. And so you can get away with things you could not do before. But there's this thing, people say that Moore's law is at an end. So we cannot trust that the hardware becomes faster and faster the way it became faster until now. And this leaves us in a little bit in a pickle, because if we cannot trust that the hardware is faster, how can we expect that we have this kind of technology transfer? And that's the reason why neural is so hyped, because it gives us a way out of the end of Moore's law. And it's probably nothing I need to convince anyone here, because right now there's a lot of research going on about neural rendering, neural materials, neural everything. I did a very rough count of, just for fun, all the publications, SIGGRAPH Asia, self-titled reflectance modeling. So they claim they do surface materials, comparison between the analytical, the non-neural papers, and the neural ones. And what we can clearly see is that the analytical material research is coming to an end. Neural is picking up, analytic is going down. And we are right in the middle of the neural research academic phase. The neural material paper we published in 2023, it was neither the first one, it was also not the last neural material paper which was ever presented. The thing which makes it kind of a little bit special, I would say, is that it is the first paper which was targeting film quality materials. And by film quality, I mean the definitions I had in the beginning. To get those materials was a fun project. We were working with our artists together and asking them to generate a number of highly detailed digital assets for this project, with the requirements that the texture resolution is high enough that from 10 centimeters distance you would not see any visual artifacts. 4K texture resolution with as many UDIMs as they liked. Arbitrary layered BSDFs. In our case, we're using the Material X layering system. no displacement, because our renderer couldn't handle displacement that well, but otherwise as many textures as desired. And the material complexity we came up with, it's comparable to what you would have in VFX industry. We have deeply layered, multi-layered materials. They're composed of multiple BSDF lobes that represent physical layers, real physical layers. We have all the imperfections. We have the dust. We have the stretches. We have the stains, all these things. And the shaders you have, if you have these materials, they tend to be much slower to execute than those we normally use in real time when we have PBR materials. And to make things work, these shaders, they would all be different as well, so it means you will have a lot of divergence in URIs. When we evaluate a material for a given shading point, we evaluate the local BRDF of incident and outgoing direction. The most straightforward approach is then to feed those to an MLP, which is tasked to predict the corresponding BRDF values. And this is exactly what was proposed by Strachmann and colleagues a couple of years ago, and which we are building on. They focused on spatially constant materials. We want to have the textual variation here. So to support the variation, we followed another paper, and what they did, they fed an additional latent code that compressed the position of the BRDF attributes. It's kind of similar to the normal graphics pipeline. So these latents, they are fetched from a latent texture, and more specifically from a latent texture pyramid. And this means that the MLP output, it can predict a filtered version, a level of detail version of the BSDF. In principle, you could train this end-to-end with the sample texels and the directions, do a random sampling of the samples, and you backpropagate through the MLP and to the texture lookup, and you're done, which is exactly what they did in the paper. But this doesn't really work well with the materials we had in mind. So in particular, the texture size which were used in the paper was 512 times 512. And the problem is for a higher texture resolution, 4K textures, the one we had, this is problematic because the same sample budget is split between way too many texels, and so each one receives fewer gradient updates, and the optimization simply doesn't converge anymore in a reasonable of time. But we can still exploit the fact that many surfaces share a lot of similarity, and so we propose to replace the latent texture with an encoder network, and that one takes all the BSDF parameters we had in the reference materials, and we're feeding it to the training. And so this way, similar texels will automatically be mapped to similar latent code. And we can see that the result is a lot better by using the encoder. So the additional network we have here and all the BSDF parameters, they're kind of heavy and we don't want to have them during render time. What we still can do is we can still explicitly generate the latent textures, use those, completely remove the encoder for the rendering, and pretty much we are done. The paper goes way into more detail about introducing a shading frame decoder and to have important sampling, how these things were done. If you are interested, I don't think they are so interesting that I want to go through them now. If you are interested, read the paper, talk to me, one of these things. The more important thing is we have this decoder, and with the decoder, we can do nice things. For example, we can adjust the decoder size to change the quality and the performance of a material. Doing material LOD is something which is rather hard with analytical materials because we cannot form them, shape them to our liking, but it's a task which is very easy for a neural network. We have another asset here. This maybe doesn't look like it, but it is significantly more complex, like the Lund teapot we were seeing before. The reason for it is that it pretty much combines the complexity of the teapot and the handle of the teapot in the same material, because we have this blend between the metal and the ceramic at the same time. The asset, again, was built with material X. In the end, we ended up with 9 BSDFs for the asset, and the asset had 6 UDIMs with 4K textures. So we can now change the size of the decoder to adjust performance and quality of the material. The numbers I have here in the upper corner, they show the total render time, not the shading time. It is a 2K frame, full frame material, rendered with a path tracer. But to be fair, it's just standalone, so the path tracer is pretty much a first hit only. So can probably ignore the path tracer. So what we can see, though, is that compared to the original material, compared to the reference material, the render time goes down. We settled to different quality sizes for the network. So we have the high quality 3x64, the medium quality 2x32, and the low quality with 2x16. And depending on the network size, performance becomes faster, becomes better, quality goes down. I'm pretty sure no one here can really see the difference between those different materials. They are there. You can see them when I start flipping between them. There is unquestionable a degradation in the quality. And I wish I could now say, well, everything works, and all you need to do is you change the size of your decoder, and it's there. It would be a lie, though, and we are not lying. So for the small networks, it is hard to train them when the underlying material is super high quality, super complicated. The larger ones, they don't struggle that much, but the very, very small ones, the 2x16, they have a hard time. And in particular, when I first tried to train this material, I was struggling with the normal maps here. The way we choose the samples, it's a mixture between uniform sampling and importance sampling, and feed those to the network. The network really didn't like it for the normal maps. Interestingly enough, by introducing more random noise into the data, we can get much better results than we had before. So suddenly, the grazing angles still work. We have good normal maps. What we did get rid of, what the network sacrificed, was the color tint in the absorption in the grazing angles. Interesting enough, we can achieve this by doing something counterintuitive and make our samples worse than they should be. This means, in the end, I mean, the sad thing is there is no solution that will work for everything. It's a little bit of fine-tuning for a specific material, but the problem itself indicates that we need better sample distributions for the training, a better understanding of the sample distribution, what's good for learning, and or a perception-based loss function, because the mathematically ideal solution is not the solution which are the best suited one for training. What we can identify, though, is what is hard to train. Hard to train, my arch nemesis, specularity and normal maps at the same time. And not just specularity and normal maps, multiple of those. That's super hard to train. A little bit more counterintuitive, saturated colors, or finding outliers in your training data. I mean, this is a data distribution problem. How do you identify which part of the material are important and which are not? And my personal favorite, mixed materials, which is something artists really like to do, combine different kind of material in one single asset, in one single material, and then you need to learn a way, way more complicated material than it should be. But what I really want to point out is neural materials, they are not an academic fantasy, they are real. They are not a research concept. They are here and there, they will stay. In particular, we tested them on large scale scenes, and we tested them with an Unreal Engine implementation in a production game engine as a concept. For the large scene training, I was using the Da Vinci scene. Da Vinci scene is a scene which NVIDIA published, free, everyone can use it. If you want to have a scene which is production-like, this is probably the best you can get because it has over 1,000 different materials. Even if I deduplicate the materials, I end up with more than 500 different materials. The only drawback might be that the materials are MDL materials, so it means omni-PBR, omni-surface, and MDL is not something which we would normally use in research. So 500 materials, this is a lot of things we need to train, even if you have fast training time. And our training time is around, it's a couple of minutes, 2 or 3 minutes per material, went way down from the hours we had in the beginning. It's still a lot of things you need to train. The thing is, do you really need to train all these materials separately? Because if you look at scenes, they share material properties, they share appearances. And so the question is, can we train materials to utilize that? And yeah, we can, because we can cluster materials into groups we want to train together. So this is a small subset of assets we have in the Da Vinci scene. And we can see there are certain similarities. So we have, for example, very specular metal materials, or diffuse-ish gray, something like the log and the ash, or the wood. All the wood assets, they look pretty much the same. Not so much for the statue or for the flower pot, but you don't need to put everything together. First, just by clustering some of the material, you can save training time, you will reduce divergence, and you will reduce the render time. There is a stop, there is an end, what you can train together though. For example, if I take the door, I've trained it 3 times. Once it has 4 materials, the wood, the 2 stones, and 1 metal. And if you, first one is I trained everything separately, second one I trained the wood on one end, and then metal, stone on the other one, and the third one was just everything all together. Again, it's a little bit hard to see here. I can flip between those. There's also an error image. What we can see is that the spec of the wood starts to change a bit. So the more materials you put into your training, the worse the training will become. But again, you don't need to train everything all at once. You can still cluster these materials separately, and this brings us to the next question. How can we decide what to train together? We want to have, you don't want to have the network becoming larger and larger and larger, because this means the render would become slower and slower. What we need the sweet spot between the size and the expressiveness of the network. And so you can cluster the materials together according to their appearance. I would not advise to do it according to material categories like leather or wood or stone, because 2 leathers can look quite differently, whereas a plastic and a painted lacquer look very similar. So we need a redefinition of appearance here concerning which features can be learned together. Future research, I don't have the solution. But what we can say at this point is, so we have on the one hand, we have the analytical materials, our traditional materials, and we use them because they have existing workflows and DCCs. They are easy to edit, even on a very fine granular level. We can use them as prior for training, and we can use them as training data itself. And on the other hand, the neuromaterials we have so far, they are baking solutions. They can encapsulate data very, very well. They can do things like automated quality approximation, level of detail simplification, compression of shaders and compression of textures. So all these things which are very hard for a human and very hard to do with analytical materials. We are not, with the neuromaterials we have, we are not replacing analytical materials. We work with them and we use them as an underlying base for the neuromaterials. Next question, which normally comes up then, is, well, can we completely, I don't like analytical materials, can I completely get rid of my analytical materials? Yeah, people do it. I mean, this is what differentiable rendering is all about. It's about getting the data from a diffusion model, for example, instead of creating it manually. You can do it from single photos, you can do it with intrinsics, with prompts. There's a variety of different ways how you can generate materials other than from within a DCC. But the problem they all share is that as long as there is inverse rendering part in the pipeline, there's almost always a simplified BSDF model which is used for the optimization. And in particular, this PBR material I showed right in the beginning is one which is used very, very often. The problem here is you are only as good, your results are only as good as your base material. And if the base material cannot capture the effect you want to do, it's simply not possible to learn it. Don't get me wrong, it's not bad what you get with these materials. So teapot here, one is the original one, the column to the right is the simplified one. So we are losing the orange peel of the top glazer, for example. Or we are losing the hue-dependent edge tints. Or just the fine structure we have in the original one, in the original teapot. Again, it's not really bad, but it's not a faithful capture of your material. So, okay, if there is a bottleneck between what we can get with inverse rendering from the analytical materials, can we then maybe completely get rid of the analytical materials and completely ditch them? Can we do fully image-based rendering instead? Well, I mean, you have to acknowledge that diffusion-based images, they became better and better. They improved over the last years. I remember everyone made fun of the 6 fingers and the 3 eyes people had. It's not there anymore. The improvements we saw within the last years were just amazing. So there is definitely a potential to create images far more realistic than what we can do, what we are willing to do with traditional 3D graphics. And especially video models, they show a great potential for us to enhance the graphics pipeline, which raises the other question. Is it time for us to ditch physics and simulations? Do we still need to understand the theory behind materials, between light transport? Should we, as a graphics community, stop teaching these things? And it depends on your view on where we are going with this technology, if these things are necessary or not. Because a lot of people also talk about using the video, especially the video models, to replace the entire graphics pipeline, the entire production pipeline for games, for films, and use instead a video model instead. What people tend to ignore who never worked in production is that this image generation is really just a very, very small part of the pipeline. It's right at the end, the rendering, and everything else before is a huge part of movie production. It's more importantly, it's not a linear thing that you say one person begins and then it goes down until we have the rendering, until we have the comp, and we are done. Now, it's an iterative process. Creating assets, it doesn't take, or creating movies itself, it doesn't take long because people are lazy, they don't know what they are doing, or that the actual craft takes long. The reason why it takes long is that we have those revision cycles, that you start with something, then you show it to someone else, and this person will kick it back to any part in the pipeline, and then you need to start again and again and again. And this goes on and on. As a rule of thumb, frames, they get never finaled because they're perfect. They get finaled because you ran out of money or you ran out of time, but not because they're perfect. So this obsession with revision is also why people normally say, okay, there are 2 things which are the make or break for image generation, a complete replacement of 3D rendering. So the controllability and the consistency. The controllability. Can I address a node, for example, that the specula from the 3rd character to the right should be a little bit tighter and just change that, but nothing else? And the consistency. Can I generate the same thing twice? Can I generate exactly the same asset, but once with water droplets and once without? So those are the things people say, okay, we need to be able to solve this. The truth is, it's really depends on the director and the artists and how they like to work, because I've seen people being quite happy with improv. Let's say it's something like you would have 2 actors reciting a dialogue 100 times, and the director just picks one because it likes it. That's the equivalent of prompting. You just try, and then you get something you like. And then there are other people who have a very, very, very focused vision, and they want to have exactly this one thing they have in their mind, and there is zero wiggle room for anything else. What I want to tell you is just the way people work, it's different, and not everyone is the same. There is no one-size-fits-all workflow that will work for everyone, and the technology needs to adapt to different workflows. It's definitely not the other way around. Technology follows the artist and not vice versa. The artist does not follow the technology. But I know people like lists and wish lists and all these things, so this is my very, very personal wish list of things which need to happen before we can see the visual fidelity we know from visual effects with the image generation pipeline. And one thing is resolution. 4K, 8K, stereo, EGSR images. And please don't tell me, well, we can up-res them, because that's not exactly the same. It always looks different. Masks way beyond what we have right now. Not just segmentation. We need masks, things for like, well, the heat pattern on the exhaust of some spacecraft, and just this one and not the other one. So very fine granular things to adjust. Deep data, and I don't mean the depth bus, I mean volumetric deep data. Things that are standard in compositing, because at the final frame, the image you see in a film, it's never directly coming from a renderer. There's always a comp department which is doing the adjustments on the image. It's also normally not an all-in-one render, where you would see everything rendered at the same time. People render in layer so that they can iterate on specific assets, on specific looks. The third thing is sharpness, crispness. Softness is amazing for Instagram. It's not necessarily great for realistic images. And then lastly, I can easily make a movie girl in a coffee shop. Creating a girl in a coffee shop with diffusion, it's amazingly easy, because these systems are trained with this kind of image. But life itself, life is raw, and life is brutal, and life is not pretty. And we need to be able to go beyond this kind of prettiness of everything is bedlick and everything has a shallow depth of field. So in a way, I don't want to say it, but ugliness. We need more ugliness. But again, this talk is really not about us answering the question, is rendering that? I'm a material person, and so I'm interested in analytical materials. Are analytical materials dead? Do we need to stop doing research about them? Do we need to stop thinking about those? And I would say it really depends. Who's the audience? Who's asking the question? Yes, I dare to say analytical materials are dead for fast graphics. And by fast graphics, I do not mean real-time rendering. This is not about real-time versus offline. Fast graphics is fast image generation in a way of iteration times. It's content creation with fast iteration time, like advertisements, product design, architectural design, the 5 minutes YouTube clip you see somewhere, or the 20-second TikTok you watch on your screen and you don't even look at what you're watching. So for this kind of applications, yes, I say analytical materials are dead and no one will use them. The other end of the spectrum, predictive rendering. And here I can say no. I do not think that we will replace predictive rendering with any video model or any diffusion models, because here it's about predictability, and it's of the uttermost importance to be able to say this is correct or this is not correct. And it's hard enough to keep track of the error, the normal error you have in your render pipeline. I really wouldn't want to have a model in there which is hallucinating data which I cannot control at all. And then in the middle, you have the slow graphics. Again, not offline rendering, but slow. I'm talking about the process of developing something. And here, I think we have room for both. I think that analytical materials and neural materials can happily live side by side. Then we can use neural materials, neural generative processes to create materials. And on the other hand, sometimes it is just easier to use traditional workflows because, for example, the material you have in mind is not in the base data your model is trained on. So you can use your traditional knowledge for those. In the end, a user, an artist, they will always use the tool which is best for the job. And so if analytic is best, you take that. If the other one is best, then you take that. The truth is, though, no one really knows. For a while, we had this thing that predictive rendering would become more and more, and people were going from, oh yeah, physically based, this is really, really cool because I can control it so much better and it's more expressive. And then we had this 2017 microfacet wave optics hypes, and then suddenly, yeah, okay, now we have diffusion and materials, and we don't really know what's going on, and we don't know what the future will bring here. What we do know, though, is that the first time ever real-time rendering, real-time graphics, and offline rendering, the development is in sync. There is no longer, okay, we have offline rendering as the test bed for real-time rendering, and then if something is proven and the hardware is fast enough, we're going to real-time rendering. This is not the case here. Neural materials, neural technologies, they are the same for both real-time and offline. And so real-time and offline, they go hand in hand. In the end, again, no one knows what's happening in the future. It is an exciting journey we are on, and only the future will know what it will bring. And with that, I think I am in time. Am I? Thank you.
Thank you so much, Andrea. Are there any
time?
Yes. I mean, yeah, so we ran a bit over time with the paper session, but that's fine. We have enough time for lunch, so we'll take our time here. No need to get nervous about that. So any questions?
Thanks so much for the talk. That was absolutely excellent. Like with like dust textures, I can't imagine how sparse that is as a texture. But I don't want to talk about representing it as texture versus geometry or particles. But how do you measure the perceptive importance of those dust particles? You can't really measure saliency. It's more of a global impact on the end user. So I was just curious if you had any comments about that. And did you have any perceptive quality measurement for the importance of subtle effects such as dust particles?
It's a good question. It's an open research question. There is nothing where I can say, yes, of course, we have the answer to that one. Right now, it's an explorative session of figuring out what works and what doesn't work.
Nice talk. It was quite informative of how production works. So how easy would it be to start with with explicitly modeling the statistics or explicitly modeling the microgeometry procedurally, and then training the materials to then approximate the results as you zoom out on them?
Great question. I think it's a very feasible approach to model something explicitly and then create your BSDFs out of that one. The main bottleneck is, of course, the modeling, because what I didn't mention is that modeling assets, modeling materials, it's a very, very time-consuming process. And even if you do it procedurally, you are then back at the problem of, it is not an arbitrary thing. You would still need to drive it with more information, for example, coming from simulation, where should be what, where would I have wear and tear, where would my microfacets be different than in other places. So from a technical point of view, yes, I think it's very feasible to do. From a content generation point of view, this is most likely the bottleneck you will have.
Any more questions in the audience?
Thanks. What would you say is the place of photogrammetry and capturing materials from the real world in all of this?
Another great question. I think it's fits right into this world, using photogrammetry as a source of data. We, as material people, we always struggle with where we get our data from. For the image models, for the video models, it's kind of easy because you can skim YouTube, you can skim the internet, and you get your data. But we don't have the data for materials, because measuring materials is a very time-consuming process. Simulating them from ground truth is even more complicated. So getting the data from photogrammetry is, at this point, very good. The question is only, how can we extract the information we really need?
Hello. I thought what you said about needing things to be uglier, that's a very interesting and I think very salient point about all this generative AI stuff. So I was wondering if you had any ideas about how you would improve the training sets for these generative models so that you can get more flexibility in sort of the aesthetics and maybe even like art style of what you want to generate?
So my disclosure, I'm not a generative AI researcher. So everything I say is take it with a grain of salt. I think the problem is that in the past, models were trained with materials from, based on being rewarded for creating pretty images. So you need to change the reward process, because I still believe that there is so much ugly data on the internet we could use for training, where it's amazingly easy to produce a burger, for example. I get surface details which are incredible if I zoom in into the image. I cannot get the same kind of thing for something like fabric. It always looks kind of off, because a lot of people most likely did photos of their burgers and put them on Instagram, and so we have the training data for that one. Ugliness, again, I think the internet is full of ugliness in the best and the worst ways. It's just rating the data correctly.
Hey, thank you for amazing talk. I'm interested when you're talking about level of detail and having smaller networks and introducing noise to reduce the perceptual, to improve the perceptual quality. How can you share some thoughts on how introducing noise to normal maps or things like that, and how you avoided some sort of what sort of problems or things that you have to do to avoid problems, introduce noise into directionality? Or
so as I said in the beginning, if you have those super complicated BSDFs and you have this very tiny network, you want to fit everything. It's a oversubscription of the network, and you need to feed the right kind of data. You need to communicate to the network the kind of data you want. The noise I introduced, I was like I'm personalizing the network now, but it was running along and training, and then you take a wrench and you put it between its legs and it stumbles and it learns something else. The noise was a way to weight down, I think it was a way to weight down the important sampled peak, and so it had less of those samples and could concentrate more on other things. So for this one, we need to understand what is good, where it's focusing on, and it's also the reason why I say the loss functions we have right now, and we are using L1, it's not necessarily the one which is best suited for the task, and that we would need more information, that we will need more information about what is visually good and what is not as good.
Any more questions for Andrea? Yeah.
Thank you for the talk. I really enjoyed it. I'm not a material person, so this might sound like a dumb question. It feels like every studio or production company probably has a magnificent library of textures they've created. Do we feel like maybe having an open, or there may already be one, library, and then training on that open library would help solve the generative AI problem?
It would be amazing if we could do this. The main problem here is the data doesn't belong to the studios, it belongs to the client. And this would mean, in particular, Disney, Paramount, Warner Brothers. And so it's not the visual effects studios like Weta, ILM, DNEG, and all the others you need to convince, it's the clients. And they are normally reluctant to give something away for everyone if it's their own.
A great presentation, Andrea. I have a question looping back on the aggregate materials you were saying that are the hardest in visual effects in a way. Doesn't their appearance depend also on the light transport? I'm talking about hair and how you resolve that, and same with sand or whatever, a sandstorm or whatever. How would you approach that with neural rendering, and how would you create a material that without knowing what the light transport simulation is at that stage?
So the materials we have, they are trained in UV space, and they don't know anything about light transport. So they will always try to be they will try to do the best they can with the worst, assuming the worst light transport situation you have. You could think about saying, okay, I have my material, I know it will always be dark in a specific room, or the light will be diffuse, and you could start baking this kind of information in. But the reason why physically based material were so convenient is because you don't need to have this kind of information. You can train it once, you can take it, and you can put it everywhere. If you think of things like porosity, hair, those materials are volumetric materials. And if you would want to have the entire, something like neural radiance caches, where you have the light transport also baked in, then it's a different kind of technology. It's not what our neural materials do. I'm always a little bit reluctant to recommend taking too much focus on the light transport, because I'm a material person, not a light transport person, and I always say someone else can figure it out.
Folks, let's thank Andrea again. Thank you so much. Yeah, so now we'll wrap up, and so I'd like to ask whoever does that on stage. Thank you.
All right, well, thank you all for your participation over the past couple of days. And we're now at the closing session. So we've got a few awards to make and then some announcements about next year. So for the Papers Awards, we'll turn to our Papers chairs, Aaron and Christoph.
Thank you very much, Christian. And first of all, I'd like to extend a very honest thank you to all of the authors who made our papers program as excellent as it was this year. I think it's no small statement to say Christoph and I were overwhelmed with what we got, and there was no question that this would be a great program. And after actually seeing them presented, we were justified in thinking that. So thank you, everyone, and everyone please clap for yourselves and for the authors of HPG 2025. So this time I'd like to briefly award the Stephen G. Barker Test of Time Award to a paper a decade ago that now has the most citations now out of any of the program of HPG 2015. Just a brief word about Steve Parker. Christian and I both know, and many people in this room both knew him very, very well. In a lot of ways, he was the godfather of the ray tracing symposium and that component of this conference. He had a very distinguished career both at University of Utah and then subsequently at NVIDIA, and he is greatly missed. So the number of citations of this particular paper is 54, which was substantially greater than the next others, although those are quite well cited in their own right. And the paper was Bounding Volume Hierarchy Optimization through Agglomerative Treelet Restructuring by, oh my gosh, Leonardo Dominguez and Helio Pedrini, both a professor and researcher in Brazil, who basically re-implemented the TRBVH and then the agglomerative extension of TRBVH by Tero Karras and Timo Ayla. And I think what made this work really, impressive in terms of the number of citations is not the fact that it was so incredibly original, although it did provide a meaningful 30% improvement on performance over the original TRBVH and agglomerative TRBVH builders, but they open sourced and published this work on GitHub. So everybody refers to this paper and cites it whenever they refer to this GitHub implementation of TRBVH. So that's had a meaningful impact, and we've reached out to these authors and have not heard a response yet, but hopefully they're unfortunately not in this room to accept the award, but we thank them very much for their contributions and to the original authors of the TRBVH work. And we'll just briefly mention the second and third place award winners of the Test of Time Award. An adaptive acceleration structure for screen-based ray tracing by several authors. And then in third place, efficient ray tracing of subdivision surfaces using tessellation caching. So thank you to these authors for their contributions. And now, last but not least, I'll turn it over to Christoph for the Best Paper Awards.
Thank you. So, as those of you who were already here in the first paper session today know, we had a vote to determine the best paper of HPG. And now we'll be handing out the Wolfgang Strasser Best Paper Award, named after Wolfgang Strasser, who is essentially the founder of computer graphics in Germany. He's also the advisor of my PhD advisor, and that's the case for, I think, quite a substantial number of people in this room, so he has had a very large influence, and we dedicated this award to him. Now we will go through this, starting with the third place. And so, all paper authors and presenters, please be ready to jump up from your seat in case you win. And now I need a little drum roll. So, the third place goes to Hardware-Accelerated Neural Block Compression with Cooperative Vectors by Laurent Belcourt and Anis Benyoub. Congratulations. Okay, moving on to the second place. I need another drum roll. The second place goes to Real-Time GPU Tree Generation by Bastian Kurt, Max Oberberger, Carsten Faber, Permin Pfeiffer, Ziad Mashi, Tabay, Dominik Baumeister, and Quirin Meyer. Congratulations to all of you. Wow, so many authors on stage. Who do I even give this to? I'll give it to Bastian. Congratulations. 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 Good work. Okay, and now we move on to the first place. The winner of the Wolfgang Strasser Best Paper Award this year at HPG 2025 is Spherical Harmonic Exponentials for Efficient Glossy Reflections by Ari Silvenoinen, Peter Pike-Sloan, Michael Ivanicki, and Derek, well, you can read his last name. And accepting the award is Peter Shirley, who was presenting it. Congratulations.
Spherical harmonics forever.
Okay, and with that, I will hand it back to Christian.
Okay. All right, very good. Congratulations to all our winners. One more award this year, and it's the Annual Chairs Award. So this is an opportunity for Michael and I, as general chairs of the conference, to recognize the contribution of a fellow committee member that really went above and beyond this year. It was actually a close race. I mean, quite frankly, any one of the folks that have volunteered this year could have been the awardee for their contributions and getting things ready and making sure things run smoothly. But this year we decided to recognize Rickard for his contribution as registrar. So come on up, please. You may be aware that we had a bumpy registration process at the beginning, and unfortunately we had been dealing with some personal issues on the committee, and it kind of fell to Rickard to fill in the gap, and he really did jump in, kind of taught himself the system, and got all of those issues ironed out, I think with very great speed. And so we're super appreciative of that, and look forward to hopefully having him participate again next year. So let's congratulate Rickard. And again, it's worth giving a round of applause to everybody on your committee this year. It's been a fantastic process. I've been chairing now for 2 years and had an opportunity to develop real relationships with these folks, and we appreciate their contribution. And again, let's have a round of applause for the entire committee. Okay, Michael has some information for you about HPG 2026.
Okay, so but before that, we do that, I would just like to take a moment and make a personal and a big thank you to Christian Gribble, who's been our general chair last year and this year, and he has done an exceptional job in my experience of organizing committees. So thank you, Christian. Okay, so I would just like to announce that High Performance Graphics will return again next year. It will be in Los Angeles, the days before SIGGRAPH. It's usually Friday, Saturday, Sunday, so that's the 17th to the 19th of July. I will be one of the general co-chairs, and we will very quickly find another general co-chair and, of course, a committee. So if you're interested in being on the committee, please do contact me. And yeah, we will have information soon. Okay. So thank you all for attending HPG this year, and we look forward to seeing you next year in LA. And now lunch is 3 floors up for those that haven't been there before.